Okay, I finished grading the reservoir draft submissions, and so now at this point you should have all of your draft phase of the project graded. Just as a reminder, the draft submissions that you did accounts for half of the project grade, and then the other half of the project grade is evaluated in the final submission. So your final submission is due before class on Monday, which means you've got the weekend to finish that up. I noticed some people have already submitted it, and that's great. But you've got the weekend to finish that, and I will be going back to see what enhancements you've made since the draft submission, if there were issues or errors that I asked you to address. Then homework 13, the last assignment, that's due on Friday the 19th, and we have our final on Tuesday the 23rd. So that's the schedule as it lies ahead. Today we're going to do one more method that helps us to assess gradually varying flow, and that's the standard step method. So does anybody have questions before we start talking about the standard step method? So what we've done so far is the direct step method. And it's useful, but it has some limitations that the standard step method is going to help us to overcome. Before we get into it, I wanted to reiterate something that I know you already got an email from the college 2 days ago and an email from me yesterday, but the first meeting of the American Society of Engineering Management is on Monday at 5. And so I'd encourage you to attend that meeting. It's at 5 o'clock. They're going to have food available, and it's just like a good thing to put on your resume that you're involved in, professional organizations, and that you did more in college than homework, that you're involved in some sort of a student club. So I'd encourage you to consider coming to that Monday afternoon. So we've been working on the direct step method. Sometimes it's also called the step-by-step method. And the problem with it is we only apply it when the channel isn't changing shape. So you'll remember that when we applied it, we had some channel that was, let's say, 2.4 meters wide, and it was a rectangular cross-section. We could use a trapezoidal channel for the direct step method, but the problem is the limitation of the direct step method is it assumes that downstream and upstream, the channel has the same width and the same shape. So let me just do a top view of a stream and show you what I mean by that. So if we're looking down from above here, and we have a stream that's flowing like this, and the same width upstream as downstream, we can apply the direct step method. So it's good for like an engineered canal. Like if you've ever flown over Florida before, so like on your way to Miami or Fort Lauderdale, you look down and there's these long straight canals. So you can use the direct step method if you've got a channel that isn't changing width. But most natural channels are changing. Like if you look down from above, first of all, they're not going to be straight like that. Natural channels are more likely to be meandering. But in one section it'll be narrow, in another section it's wide. So, the width is changing. But then in addition to that, at one location, if you looked at it, maybe it's trapezoidal with 1-to-1 side slopes. And then in another location, maybe it's not even trapezoidal. It could be that the channel looks like that. And then, just to be far-fetched about it, maybe in one section we have a rectangular channel. So the direct step method couldn't handle any of that. It has no way to account for changing widths and changing shapes, which is most of the time. For most natural channels, you've got an irregular cross-section. So we need a tool with a little bit more sophistication than we've been using so far. And the standard step method is that tool. It can be used regardless of what the shape of the cross-section looks like, and it can be for a changing shape of a cross-section. So here I'm giving you an alert. This red alert here means that 1 and 2 are going to mean different things than they've meant for everything until now. Like until now, 1 always meant upstream and 2 always meant downstream. When we're working on the standard step method, 1 and 2 doesn't mean upstream, downstream. Now it means 1 is the location where you know something, like that's where you know the depth, and 2 is the location where you're trying to find what is the depth. So it's the location with the unknown. So please keep that in mind when we use the standard step method. So the standard step method is looking at gradually varying flow, and what we're going to do is we're going to try and assess how does the energy change between 2 points. So here in this diagram, for example, we're seeing these new numbers applied for the first time. Like we can see that water is flowing from the left to the right. Water flows downhill, right? But 2 is the upstream section and 1 is the downstream section. We've never seen that before, where like the upstream section was referred to with the number 2. So what that means is here at location 1, we have a measured depth. So at location 1, we know, for example, if there's some elevation data, like for example, sea level is a most common elevation data. And we know that the bottom of the channel is some distance above sea level, and so that would be Z1. Z1 is from our elevation datum to the bottom of the channel, and then we have a measured depth, Y1. And maybe we have it measured because there's a stream gauge there. It could be that like there's a sensor that every so often takes a measurement of what's the depth of water. So we know the depth at 1, and if we know the flow velocity, which we can derive from a variety of ways, but let's just say that we know the velocity or the velocity head. So we could know the height of the total energy line there. The total energy line would be the water surface elevation. So here WS means Z1 plus Y1. It is the distance from the elevation datum to the water surface. So it's no big deal. It's just saying, you know, what's the elevation above sea level to the water surface. And then we've got the elevation head, which is, the velocity head, which is v squared divided by 2g, or like q squared divided by 2ga squared. But what this method says is let's keep track of all of the energy. And so we know that all of the energy has to be accounted for some way. And here at location 1, what gets us to the top of that line? Where is the energy? The energy is the water surface elevation, so that gets us from the datum up to here, plus the velocity head, so that gets us from the water surface up to the total energy line, and then the head loss. So head loss is the distance between this original amount of energy at location 2 and the total energy line. So the head loss would, if we had steady uniform flow, be the same as delta Z, but the head loss here can be estimated with Manning's equation. We're going to take that into account in the method with Manning's equation. So just basically we're saying all of the energy is accounted for at 1 that was upstream here at 2. So the energy at 2 was the water surface elevation plus the velocity head. So some of the energy got transferred into head loss, and there may also be a change in the velocity head between the 2 points, because the velocity at 1 and the velocity at 2 aren't necessarily the same. But the heart of this method is an energy balance. So there's a template file that I've put onto Blackboard that we're going to use for today's example. And built into the template is the idea that we're trying to track where the energy is going as the water flows between 2 and 1. So does anybody have questions so far about like the background of the standard step method? So here's the method. This is what I've built into the template. We're going to assume a water surface elevation for 2. So why do we assume? It's because we don't know what is the water surface elevation at 2. We know conditions at 1. We know the depth of the water at 1. We know the velocity at 1. We're trying to find out how deep is the water at this unknown location. And so if we have subcritical flow then most of the time what we'll be doing is working upstream if we've got subcritical flow. We'll apply this method to start at a location that's downstream and known, and we're working upstream to find out like how far is it to a certain depth upstream when the shape is changing. Remember, that's why we use this method instead of direct step, is because maybe the width of the channel is different, or it's going from rectangular to trapezoidal. So we'd only use the standard step method if the situation was more complicated than we could handle with direct step. Okay, so we're going to just start with a guess. Then, based on the guess, we'll find out how much head loss does that mean there was. And so the observed head loss is the difference between the upstream, or the unknown energy, and the known energy. Then we'll determine something called the calculated head loss using the slope of the energy grade line. So S bar of F, that's saying at the midpoint between 1 and 2, what's the slope of the energy grade line? And we rearrange Manning's equation to find the slope of the energy grade line. So this is just Manning's equation. We've seen this before, solving for S. So the midpoint energy grade line slope multiplied by the length between two sections plus a C value times the difference in velocity heads. That'll give us the calculated head loss, and then we're going to compare what's observed to what's calculated, and if they're not the same, then that tells us we have to make an adjustment, like our guess wasn't correct. Do you remember this numerical technique we've used all through the semester where we didn't know the answer to something, so we made a guess, and then we tried to improve our guess, and we gradually worked towards convergence, which means that the guess finally will become correct by making small changes along the way. So what we'll do is, if we don't have a match between the observed and the calculated head loss, then we'll estimate a water surface elevation at 2 using this formula with the calculated head loss. So that'll allow us to make an adjustment. Then we'll update the water surface elevation by basically splitting the difference between what is calculated from this formula and our previous guess. So we split the difference, and then we repeat this whole cycle by recomputing the observed and the calculated head loss. And so we keep repeating that cycle until the observed and the calculated head loss do converge. So this is kind of the background rationale, or the background algorithm that's applied within the spreadsheet. Oops. All right. So here's the example. We're going to spend the remaining 30 minutes of our class time just going through this example. And so I want you to try and think in 3D. At a certain location, section 1, we know the water depth is 5 feet. So at section 1, you can see the bottom width of a trapezoidal channel is 25 feet. And then it's got 1 to 2 side slopes. So 1 unit of vertical, 2 units of horizontal. So it's pretty wide. But what's happening is that over the course of 1,000 feet, these side slopes are basically becoming vertical. So it was originally, at the downstream section, it was trapezoidal, but the side slopes are getting steeper and steeper and steeper, and then by the time we get to section 2, those side slopes are all the way vertical. So for example, halfway at a location that's 500 feet upstream, instead of being 1 to 2 side slopes, it would be 1 to 1 side slopes. And then it's gradually becoming vertical. So it's going through this linear transition. It gradually increases. And so we want to find out, how deep will the water be upstream at section 2. So here at invert, where it says invert equals 5 feet, that's defining the delta Z for us. So that's saying if this is our elevation datum, say sea level, the bottom of the trapezoidal channel is 5 feet above sea level at section 1, and at section 2, which is upstream, then the elevation of the bottom of the channel is 7 feet. So that makes sense that it would be higher, because water's flowing, in this case, from section 2 down towards section 1. In this In this example, we've got subcritical flow. So section 2 is an upstream location, section 1 is downstream. So basically, we want to find out what's going to be the new depth. If this is a channel that has an N value of 0.05, and then the expansion coefficient, the C value here, that refers to some energy losses that occur as the channel section changes. The expansion coefficient is 0.3, and then we're putting 1,000 cubic feet per second through this channel. So that's the setup. Anybody have questions with the setup? In your mind, can you kind of visualize what's happening? Where, from the perspective of the water, actually, the water is flowing through a rectangular channel to begin with, and the channel is gradually getting wider as the water's flowing downstream. Because the water starts at section 2. So water's going through a rectangular channel, and suddenly the walls start laying down until 1,000 feet downstream, it's now trapezoidal. So it's what we want to know is what was the water depth upstream before the channel started transitioning into trapezoidal. All right, so I think I've put this template file on Blackboard. Let's pull it up. And if you've got your computer, I hope you'll follow along today. It'll be, I think, easier for you to do the homework if you've had some in-class experience using the template file. Oh, I guess I didn't put the template on there. Let me do that now then. All right, so I've put all the formulas, and here's a reminder of what things look like. And you can see here from the sketch, we're trying to find out what is Y at section 2. How deep is the water at section 2 is the ultimate thing we're trying to answer here. And each row is a different iteration. So when we were doing the direct step method, we broke the segment up into lots of different pieces. Remember, in the direct step method, we'd use it on something like it's shallow and then it's getting deeper. And so we broke it up into sections like this. This was direct step. And so each row meant like this is a row, that is a row, that is a row, this is a row. Here, each row doesn't mean different segments of the flow. We're just only going from one spot to the other. Each row means like a different guess. So if you were doing this method for like a real natural channel, you'd only apply it for a small section. Like the distance wouldn't necessarily be, you wouldn't do 1,000 feet for a single step. We can get away with it here because it's a prismatic channel that's changing gradually. But in the real world, you'd have a different spreadsheet for each segment. Like if you went from here to here, you'd have one spreadsheet. From here to here, you'd have another. So you'd need to break the channel up into a lot of different sections. So we're doing this just acknowledging that this is like a linear change in shape that in reality would require us to do a different page for each segment of the channel. Okay, so the first thing we got to do is put in some of the known section details. So what do we know at location here at section 1? Let me make it a little bit bigger. So we know at section 1 the flow depth is 5 feet. So just put in 5. The area is going to be 5 times 25, and then the area of the sides as well. So if we have The depth is 5, 25 on the bottom. 2 to 1 means it's 10 on each side. 2 to 1 side slope. So we've got the area is 5 times 25 plus 5 times 10, because that's the area of the two side triangles added together. So the area is 5 times 25 plus 5 times 10. 175. Good. Okay, what is the velocity at that first section? By the way, maybe I ought to put some of these details in here as well. The flow rate is 1,000 CFS. The end value is 0.05. Z1, the distance from the datum to the bottom of the channel at location 1 was 5 feet. And then here at section 2, the invert elevation above the datum is 7 feet. The C value, which is a coefficient that talks about energy loss due to the shape transition. In the problem statement, it told us it was 0.3. And then the length between these two pieces is 1,000 feet. All right. So the reason why I wanted to have the flow rate is velocity. V is Q divided by A. So V equals this flow rate. Anchor the reference there because I'm going to come back to it. Divided by the area. Okay, good so far. Wetted perimeter. Okay, we want to know what is the wetted perimeter distance. And so it's talking about the length of the side slope plus the bottom. And we can go to table 10.1 or we could calculate it manually. So for example, this distance is the square root of 5 squared plus 10 squared, and there's 1 on each side, right? So the wetted perimeter is square root of 5 squared plus 10 squared. And we need to multiply that by 2. Because there's 1 on each side, plus 25. And that gives us the wetted perimeter of 47.361. So hydraulic radius is area divided by wetted perimeter. So area divided by wetted perimeter. Okay, so we've got our hydraulic radius. All right, now energy. Energy exists at section 1, which is the downstream section. It is the velocity head plus the delta Z and the Y. So we need to add together the Z1, Y1, and velocity head. So it's equal to Z1, which I'm referencing up in the top here, plus Y1 plus velocity head. So V squared divided by 2G. So I've got V referenced here. So V squared divided by 2 divided by G, 9.81.
Got a star there where you need a plus.
Let's see.
You've also got gravity metric instead of...
Oh, traditional units. Good catch. Yeah, so here it should be plus. So I'm doing elevation, water depth, plus velocity head, and then we're in traditional units, so 32.2. Thank you for keeping me honest, guys. Appreciate it. All right, so our energy at 1 is 10.507 feet. Okay, good. Now, based on all this, the slope of the energy grade line at the known section, we've rearranged Manning's equation. We're going to solve for that at location 1. So you can see I've got the 1.49. That's because we're in traditional units. So we have that prefix associated with Manning's equation. So equals n times Q divided by 1.49 times the area times the hydraulic radius to the power of 2/3, so 0.66667. And then close parentheses twice, and all of that is to the power of 2. So we close parentheses once to get out from underneath the denominator, and then the other time to finish the expression, and then we square all of it. So the slope of the energy grade line at the known section is 0.00644. Good. We're going to do multiple rows, but at the known section, nothing's going to change. It's always going to be these values. It's just at section 2 where we've got some guesses that are always going to be changing. All right. So what's happening at section 2? We have to start with a guess of how deep the water is. Let's say that it's a little bit deeper than it was at 1. Because, at section 1, there's a lot more flow area due to the sides, right? So at section 2, we've only basically got this part of the channel. So it stands to reason that probably the water is deeper at section 1, especially because it's subcritical. Like when it went like that, it didn't have to be as deep as it was before. So let's say 5.1 as our first guess for the depth here, 5.1 feet. And it's probably more than that, but it's fine as a starting point. So what is the water surface at 2? Water surface is defined as y plus z at that location. So it is what of our guess here plus z2. And I want to anchor the reference up here to z2 because z2 isn't going to change even though for each row we may have a slightly different guess for y2. So the elevation of the water surface at 2 is 12.1 feet. Okay, the area here, it's rectangular, so the geometry is a little easier. Area is just width times depth. So the width of the channel we can see is 25. 25 times the depth of flow, 5.1. So that's the cross-sectional area. The velocity at 2 is the flow rate. Anchor the reference because we're going to want to drag this down into different rows, and we always want it looking up here at Q, divided by the area. So 7.84 feet per second. Does anybody have any questions so far? We're just basically, what we're doing right now is we're trying to calculate how much energy is there at 1, how much energy is there at 2, and do the head losses that are implied by these estimates match? Remember, that's kind of the underlying rationale is we're looking at head loss from 2 different perspectives. How much head loss is observed, how much is calculated, and do both of those perspectives match? If they don't match, it tells us our guess has to change until we get that it does match. So we've got a velocity, let's see, wetted perimeter is going to be 25 feet for the bottom, plus 2 times the depth for wetted perimeter. So 25 plus 2 times whatever depth we've assumed. That gives us the wetted perimeter 35.2 for now. Hydraulic radius is defined as the area divided by the wetted perimeter. Okay. And now how much energy is there at 2? So E2 is just going to be, once again, Z plus the depth plus the velocity head. So it is, well, by the way, water surface already is Y plus Z. So I could just say it is water surface, and now I have to add on the velocity head at 2. So plus V squared divided by 2 divided by 32.2. I almost did 9.81 again. Would you have caught me a second time? All right. Yeah, you get in a rut sometimes, right? Okay, so the amount of energy at 2 should be 13.055 feet. And again, we're going to apply Manning's equation to find out what is the slope of the energy grade line at location 2 based on this assumption. So this is all a big what if for now. So let's put in Manning's equation, solve for slope of the energy grade line equals parentheses n times q divided by 1.49 times the area of 2 times the hydraulic radius to the power of 2/3, so 0.66667, and then close parentheses to get us out from underneath the denominator, close parentheses again to finish the expression, and then to the power of 2, because we need to square it. So the slope of the energy grade line, 0.0145. All right. Now the observed head loss that we want to calculate is, we've got the formula for that up here at the top. Observed head loss is just E2 minus E1. So for me to calculate this observed head loss, I'm saying equals E2 minus E1. So according to these calculations, at location 2, which is the upstream, there was 13.06 feet of head of energy. And at location 1, it was 10.5. So that means that as the water was flowing from 2 towards 1, it lost 2.548 feet of head. And so now, what about S sub F bar? That's just the average of this one and that one, because this is the slope of the energy grade line at location 1, at location 2. The bar here, that just means the average. S sub F bar is the average. So it is location 1, energy grade line slope, plus location 2, energy grade line slope, close parentheses, divide by 2. So it's the average. So we already previously did the observed. Now what about the calculated head loss? So I'm going to use this formula for the calculated head loss. Okay, so it's going to be, I kind of wish that I had already created a column that had the velocity head instead of just the velocity. You know, because so far I've got the velocity at 1 and the velocity at 2. It'd be nice if I had the velocity head. It would make my formula a little simpler, but it's all right. We'll get through it. So equals slope of the energy grade line at the midpoint. Okay, so it is this S sub F bar that we just calculated multiplied by the length of the section, which is 1,000 feet. So this reference over here, L equals 1,000 feet. I need to press F4, so I put in the dollar signs and always refer up to that 1,000-foot distance. Plus the C value. So I want to anchor the reference up here to 0.3. And now I need to multiply it by the absolute value, ABS, of the velocity head at 2 minus the velocity head at 1. So I'm going to say, here's the velocity head at 2. It's V squared divided by 2 divided by 32.2. Okay, so that gives me the velocity head at location 2. And now minus, click on the cell for V1, squared divided by 2 divided by 32.2. Close parentheses, and with any luck, this has given us a calculated head loss of 9.579 feet. Okay, now, if that is the calculated head loss and this is the observed, they don't match, right? So our guess wasn't correct. So we're going to want to adjust our guess. And you maybe would be tempted to say, well, why not just do a goal seek and solve for whatever depth gives you zero difference between the observed and the calculated head loss. I don't remember why that won't work, but it won't. We'll try it later, but it won't work. So we have to do it a little bit more complicated. We have to calculate the new water surface elevation using this. So water surface to calculated is going to be water surface at 1 So water surface is defined as, do we have water surface at 1 as a cell? We don't. Water surface at 1 is just the depth at 1 plus Z1. So we'll have to put that in manually. So Y1 plus Z1, anchor the reference because we're going to drag this down. So that gives us water surface at 1 plus the velocity head at 1. So plus V squared divided by 2 divided by 32.2. Okay, so that gives us the velocity part of it here, plus the calculated head loss. So that, my formula is centered, so I can't click on the location, but I can type in T30, and then it'll refer to the correct location for the calculated head loss, and then minus the velocity head at 2, minus velocity at 2 squared divided by 2 divided by 32.2. All right, so our calculated water surface elevation is 19.13. The updated, here's how we do the updated. We just average this previous water surface elevation, which was this one, 12.1. We average the previous one and the calculated one. So it is previous plus calculated divided by 2. 15.62. So just to show us whether we're converging, we can calculate like the percent difference between the updated and the original water surface. So for instance, the percent difference would be the new minus the old divided by the new times 100. And what we're going to look for is the percent difference to get down below 1% to indicate convergence. We could also just see that eventually we're going to get to the point where observed and calculated match, and then that tells us that the solution's converged. But it's just another way for us to see that our guess is progressively getting better is the percent difference will become smaller from row to row. Okay, so this is what we're going to use to determine the new guess depth. So we're starting on another row. We need to have all the same values for the known section. So like, let's just copy the known section down. What have I done? So select all of this, and if we just drag it down, I think we'll, no, something's not referenced.
Your slope values, the Q isn't locked in for both the slopes.
Which cell?
It'd be G29. The SF1 and the SF2, your Q values aren't locked in.
Flow rate. Okay. Thank you. So here I should do F4. Yep. That's right. And then that'll allow me to drag it down, right?
That's the same for SF2 as well.
Okay, so SF2, the flow rate there should be anchored. Thank you. All right, so let's see if the knowns should all be the same. Yeah. So just drag it down through the bottom of the page. Oh, look at the Y though. It should stay, instead it's counting, Excel automatically increases by 1. So just make sure it always says that the depth at 1 is 5. So 5, area is the same, velocity is the same, wetted perimeter, hydraulic radius, all of it's the same. Okay, so what is going to be our next guess of Y2? We're going to use this as the basis. So if water surface is Y plus Z, then what that means is Y equals water surface minus Z. Okay, so this new Y is going to be the water surface minus Z2. Anybody have questions? All right, so this is where if we've typed things in correctly so far, this is really going to speed up. Oh man, it's 11:49. Let's see, how much does it speed up? If I just drag everything down and like this, drag everything down. How much does it speed up? Is it converging? Yeah. Look, it's not changing anymore. The actual correct depth is 8.05. So, boy, I'm glad it speeds up because we're out of time. It's 11:49. Basically what you do is it just automatically self-corrects as long as it's getting the Y for the new iteration. It's looking at the water surface from the previous iteration. So the answer is, here at the upstream location, the depth is 8.05 feet. All right, 11:50, we're out of time. Remember that Monday, your project is due, and also Monday, we're having this ASEM meeting with free pizza. So have a great weekend. I'll see you on Monday.